This is the real-time clock circuit, which outputs the real time on a 4-digit 7-segment display. The circuit works using I2C communication from the Tiny85 microcontroller, which is the master, and the display as a slave. The shift register is acting as the intermediary. The parts used in this project are shown on the right. This RTC breakout board, which consists of the DS1307 timekeeping chip, ensures that the time is accurate. This board above the AT Tiny85 chip is connected to the SparkFun header cable to upload code to control the time. The first shift register controls each individual segment of the display, A to G, and since there are 7 segments, it uses 7 bits, 1 bit for each segment. The second shift register controls each digit and uses 4 bits, from QE to QH, and they're connected to the 4 PNP transistors, and since the display is common anode, it can only be high when it receives a low signal, hence the transistors. Finally, the colon flashes as it is wired to the square wave pin on the RTC breakout board. The display shows that the time is currently 3:17, and this can be verified on my iPad, which should show approximately the same time. So I can get a check on iPad, and it says that it is 3:18. Now onto the software component of the project. First, the segments A to G, which correspond to different binary values for each decimal value from 0 to 9, are mapped onto a segment array as shown in the image. For instance, to show the number 9, segments A, B, C, D, F, G need to be high, which are represented by 1s. Next, the time variables from seconds to year are defined. Another array called buffer is created as an intermediate data holder for each digit. Data, clock, and latch are set as outputs. I2C communication begins, and the function setTimeDate is called, which sets the time. In the void loop, after the time has been set, 2 functions are repeated: getTimeDate, which updates the time/buffer array, and showTime, which displays the time on the display. To ensure the time on the display is consistent with the real time, time and date macros are used with the ss_scanf function. Then the values for the seconds, minutes, until the year are written to the RTC device on the breakout board via I2C protocol from decimal to BCD in binary coded decimal. Next, the getTimeDate function is invoked and another I2C session begins. Data starts being read from the first required register, and the RTC address is told that 2 bytes of information is required. Then the minutes and hours are collected from the RTC, and since they are in BCD, they must be converted back to decimal for output on the display, so they can be understood. Then the clock is set to be on a 12-hour basis, and each value in the buffer array is set to a binary value in the segments array, with each buffer value associating to 1 digit on the display. For instance, if the hour was 10, then the second value in the buffer array would be 0, since 10 mod 10 is 0, and the third value would be 1, since 10 divided by 10 is 1. This same process is repeated for the minutes. Finally, the showTime function is called, which outputs the corresponding decimal value for each digit on the display. The bits are shifted out to the shift register, and since they use the PNP transistor, which is active low, the unary operator is used, which inverts the bits. Then the values for the minutes and hours are shifted out byte by byte, outputting the real time. The time delay allows for persistence of vision, which means all the digits are simultaneously visible even though they turn on one at a time. The 2 functions at the bottom allow for easy conversion between BCD and decimal for the RTC device. Here's a full schematic of the project. And here's the encased version of the project.